Hello and welcome back. We'll continue looking at triangles in this video, and we'll use triangles that are somehow alike to be able to deduce information about the second if we know a little bit about the first one. So triangles that are the same shape and size are called congruent. These are quite nice. By same size, I mean all of their side lengths are the same, and by same shape, I mean all of their angles are going to be the same, as in the same as one another. So for instance, we could have a right angle triangle with, say, 3 different side lengths, with a scalene triangle, and maybe we could angle that in a different way and reflect it. This is not going to be a perfect drawing, but if we had all the 3 same side lengths and the same angles in here, these are congruent triangles, but they may be in different places, reflected, rotated, and so on. So if we knew a little bit about this triangle, we could know something about this triangle as well. Triangles that are the same shape are called similar, but they don't have to be the same size. So for instance, here are 2 equilateral triangles. They have the same side lengths, all 3 of their sides are the same. And we'll notice that they are the same shape, as in all of their angles are the same. All 3 angles over here are 60, and all 3 angles over here are 60, but they aren't quite the same size. And what's nice about this is, as long as all of the angles are the same, their side lengths are going to form perfect ratios with one another. So their sides are going to be proportional, and we can exploit this to learn about similar triangles. So let's do an example here. So let's find the missing measurements in the following similar triangles. So in this example, we have. I also want to stress that these are 2 parallel lines, and then we have a line coming up, a line coming up there. So we have this triangle up on top, and then we have this triangle on the bottom. So these are going to be similar triangles. This is what we're told. So when they are similar, we know that they're going to have the same angles but different size sides. So for instance, we know that this angle here and this angle here are going to be the same because they are opposite angles. They're just on the opposite of 2 intersecting lines. So this is also going to be 100 degrees. This is going to be 30 up here. And because these are 2 parallel lines and this line is coming up, we know that this is also going to be a 30-degree angle. And then lastly, 3 sides, the 3 angles in a triangle are going to have to add up to 180. So 30 plus 100 plus something else is going to have to equal 180. So we know that this is going to be 50 degrees. So we can just start filling this in. So we'll use 3 there. And this is also going to be 50. For the same reason that both of these are 30, we've got parallel lines, a line dividing it up, and these are going to be sort of opposite interior angles. So we know that these are going to be the same degrees. So this is going to be 50, this is going to be 50. What's left to do is to do the side lengths. So when we look at these, our side lengths are going to be proportional to one another. So the way that I will designate the sides is we have the side that's opposite the 100-degree angle. This is going to be 4. And then down here, so we've got the smaller triangle on top, and then we'll have the bigger triangle on bottom. So the side opposite the 100-degree angle is going to be 6. So the ratio of 4 to 6 is going to be the same as the ratio for all the rest of the sides. So for instance, this side length, which is 2, which is opposite the 50-degree angle, is going to be proportional to the side that's opposite the 50-degree angle down here. So where it was 2 in the smaller triangle, I don't know exactly what length this is. So let me call this x for now. And then over here, this side length we don't know yet, so I'll call that y. And this is opposite the 30-degree angle. And up here, what's opposite the 30-degree angle is the 3. So notice we've got all the small triangle values on top, we've got all the bigger triangle values on the bottom, and this is something that I could solve. So let's just look at the first two fractions to begin with. So we've got 4 over 6 is equal to 2 over x. I can simplify this. If I multiply both sides by 6 and both sides by x, just cross multiplying, I get 4x is going to be equal to 12. So x is going to be equal to 3. That's nice. I know that this side length here is going to be 3. So we're well on our way. So this is going to be 3. And then this last one, y here, again, these ratios are going to be the same. This side length is 2 to 3, as 3 is to what? And again, I can cross multiply, so it's going to be 2y is equal to 3 times 3, which is 9. So y, after I divide by 2, is going to be 9 halves. Cool. So this side length over here is going to be 9 halves. So these are similar triangles. When we look at the angles, they are all the same. We've got 100, 30, and 50. And then the side lengths are all, the small side lengths are all going to be 2/3 of the big one. So 4 is 2/3 of 6, 2 is 2/3 of 3, and 3 is 2/3 of 9 halves. So this is all using ratios and proportions. Here's another example, and here's a little bit more specific. We have x here, and I want to figure out what x is. And we're being told that we have a couple similar triangles. So we should find which triangles are going to be similar. So here we have a small triangle in there. And we have a slightly bigger triangle that extends all the way from that point up here, down, and over. And it turns out that these are similar. I forgot an important piece of information here. How can I tell that these are similar? Well, similar triangles need to have the same angles, right? Well, there are both 90-degree angles, which I should have included from the beginning. And this angle is going to be the same for both triangles. It's the same angle. It's literally the same lines that connect there. And then up here, if both of these are at both of our triangles have a 90-degree angle and have this degree angle, they both have to add up to the same angle in the other one. So these two angles are also going to be the same. So we need to find a ratio. We need to find a proportion to be able to describe the relationship between the sides of our true triangles. So for instance, we have this side on the bottom, so in between the 90-degree angle and the one that they share. For the small triangle, that's 20. For the big triangle, it stretches all that 20 plus another 10. So again, on the small triangle, this side down here is going to be 20 long, and for the big triangle is going to be 30 long, 10 plus 20. Then for the side opposite of the right angle, the small triangle is going to be 25, and the long side is going to be x plus 25. And now all we have to do is solve for x, which will just be a little bit of algebra. So again, we can cross multiply to get 20 times x plus 25 will be equal to, oh, this is 30 and that's 25. So I'll just write 30 times 25. In order to solve for x, I need to divide both sides by 20. Let's write this down. So I have x plus 25, I'm running out of space, is going to be equal to, I can cancel a few things out. The 30 and the 20, that's just going to be 3 and 2. 3 times 25, well, that's 75 divided by 2. So x is going to be 75 halves minus 25, which 25 is 50 halves, so x is going to be 25 I'm going through the algebra quite quickly, but this is the important part right here. Maybe I should do this in a different color. This is the important part right here, setting up our ratios correctly. So again, where do these come from? We have our small triangle and our big triangle. The 20 is the side between the right angle and the angle they share in the small triangle. That same side in the big triangle is going to be all the way 10 plus 20. For the small triangle, the side opposite the right angle is 25. For the big one, it's going to be 25 plus x. And then all we have to do is solve for x, and we have that. The last question that I want to look at is this one. This comes, there's a question in the homework that's a lot like this, and I have to caution you, there are some hidden assumptions in here. But I'll draw a picture and sort of explain what's going on. So a tree is going to cast a shadow of 50 feet. So I can draw, say, like, we've got our tree, very bad tree, and it's casting a shadow. And our shadow is going to be 50 feet long. So we've got the sun, and it's shining out there. This is how long the shadow is going to stretch. And then we have a 9-foot pole is going to cast a 14-foot shadow. And we want to use, okay, so sorry, this is a 9-foot pole and it's casting a 15-foot shadow. And we want to use this information to find the height of the tree. And what's sort of implied here is that these triangles are similar. This shadow is going to be, so we're assuming a couple of things. One is the tree is going straight up, and the pole is going straight up. Okay, those are some assumptions. We're also assuming that the sun is at the same height in the sky, and the tree and the pole are almost in the same place on Earth. If they're in different places on Earth, Earth is round, so they'll be pointing in slightly different directions. There's a lot of assumptions here, so we're just going to say the tree and the pole are nearly in the same place, and they're both pointing straight up. All assumptions aside, that means that we have similar triangles, because the sun is going to cast a shadow in the same direction for both of them. So these are similar triangles. So that means that, okay, so these angles are going to be the same. These angles are going to be the same. So now the 15 feet over here on the small triangle is going to be the same as 50 feet on the big triangle. This ratio is going to be the same as 9 feet on the small triangle to the height of the tree. Maybe we'll call that t over here. And again, all we have to do is solve this for t. And this would just be a little bit of algebra. I can do that off to the side. I didn't leave myself a whole lot of space. Cross multiplying, we have 15t equal to 9 times 50, which is 450. Yes, and dividing by 15, we will get 30 feet. So this is going to be the height of the tree. Again, everything comes from drawing the triangle and noting where the similar triangles are and what ratios are going to be preserved. The 15 is to 50 as 9 is to t, and we can solve for t.